Dear students, today we discuss the maximum likelihood estimation of the k-variable model in matrix form. We have already discussed the method of maximum likelihoods and maximum likelihood estimation of a two-variable model in a previous class. Now, to generalize it and to see how the maximum likelihood principle, the method is used to estimate a k-variable model, we adopt the matrix approach. And as we have seen in a previous class, if x is a vector of random variables, x1, x2, etc., xn, x1, x2, etc., xn, then mean vector mu is given as mu1, mu2, etc., mu. And the variance covariance matrix of x is expected value of x minus mu transpose, denoted it as sigma. X is a vector of random variables with the mean vector mu and variance covariance matrix sigma. And we write it as x the shorthand form. You read it as the variables in x is distributed according to the multivariate normal law with the mean vector mu and variance matrix sigma. The variables in x is distributed according to the multivariate normal law with the mean vector mu and variance matrix sigma. That is the joint PDF f of x is equal to f of x1, x2, etc., x. And this is the compact way of writing the multivariate distribution on the assumption that, remember this, if x is a vector of random variables with the mean vector mu and variance covariance matrix sigma, then these random variables will have some multivariate PDF. This multivariate PDF is written as fx is equal to f of x1, x2, etc., xn. And the most important multivariate PDF is multivariate normal PDF. Multivariate normal PDF, and this multivariate normal PDF is written as fx is equal to 1 by, this we have written earlier, 2 pi raised to n by 2 raised to half expected minus half x minus mu sigma inverse x minus mu transpose 1 by 2 pi raised to n by 2 determinant of sigma, the variance covariance matrix, raised to half expected minus half x minus mu x minus mu transpose sigma inverse x minus mu. This is the multivariate normal PDF. And we write this multivariate normal PDF compactly as and sigma. And as we have stated earlier, if there is only one random variable, then we have what is known as the univariate PDF. The univariate PDF, which we have discussed many times, so I am not writing it again. Its compact form is x is normal with mean mu and variance sigma square. X is a single random variable. So this is the general form of the multivariate normal PDF. And a special case is when the variance of all these random variables are same and pairwise they are uncorrelated. X consists of n number of random variables. If the variance of all these random variables is same, so sigma square, and if they are pairwise uncorrelated, then sigma becomes sigma square I, sigma raised to determinant of sigma becomes sigma square n. Sigma inverse is equal to 1 by sigma square I. Sigma becomes sigma square I, determinant of sigma becomes sigma square n, sigma inverse is 1 by sigma square I. This also we have discussed earlier. Then this fx becomes fx is equal to 1 by 2 pi raised to n by 2 sigma raised to n expected minus half minus half into sigma square x minus mu transpose x minus mu. X minus mu transpose x minus mu. So this is a special case of this in which the variance of all the random variables are same and they are pairwise uncorrelated. Actually, in this case, the multivariate PDF is a product of n individual PDFs. Multivariate PDF is a product of n individual PDFs. And as we have written earlier, fx is equal to f of x1 into f of x2 into etc. f of x. And this we have written earlier, f of x is equal to f of x1 into f of x2 into etc. f of xn. And in matrix form, this is the formula. And if the variables are pairwise uncorrelated, then with the same variance and normally distributed, then it means that variables are independently distributed. This is a property of normally distributed random variables. For the normally distributed random variables, zero correlation always implies statistical independence. Now let us illustrate the method of maximum likelihoods in the context of a general k-variable model. Our model is y is equal to x beta plus u. Y is equal to x beta plus u with the u normal with the vector 0, sigma square I. U is distributed according to the normal law with the mean vector a null vector and a variance covariance matrix sigma square I. And the multivariate normal density for U can be written as f of U is equal to 1 by multivariate normal density for U can be written as 2 pi into sigma raised to n by 2. This is same as this 2 pi raised to n by 2, sigma raised to n by 2, two pi sigma square. So sigma square by n by 2 expected minus half into sigma square U transpose U. The multivariate normal PDF for U. U is the vector of random variables U1, U2, etc. Un is. So 2 pi raised to n by 2 sigma raised to n minus 1 by 2 sigma square into x minus mu transpose U transpose into U. That is the multivariate normal density for U. Now we define a transformation from U to Y. We define a transformation from U to Y. Now, the assumption of multivariate density for U also implies multivariate density for Y, and this transformation can be written as Fy is equal to Fu into dou U by dou Y. The transformation from U to Y, since we assume multivariate normal density for U, it also implies multivariate normal density for Y. And the transformation from U to Y is Fy is equal to Fu into the absolute value of dou U by dou Y. Now let me say what is this dou U by dou Y. This can be written as dou U1 by dou Y1, dou U1 by dou Y2, etc. dou U1 by dou Yn. Then dou U2 by dou Y1, dou U2 by dou Y2, etc. dou U2 by dou Yn. And the last one is dou Un by dou Y1, dou U2 by dou Un by dou Y2, etc. dou Un by dou Yn. Absolute value of the determinants. Absolute value. This dou U by dou Y is the absolute value of the determinants formed from an n into n matrix of partial derivatives of the elements of U with respect to Y. Now, the absolute value of this determinant is known as Jacobian. The absolute value of this determinant is known as Jacobian of the transformation from U to Y. Absolute value of this determinant is known as Jacobian from the transformation from U to Y. And consider this model. Y is equal to beta 1 plus beta 2 x plus U, and U is equal to y minus beta 1 minus beta 2x. Now, if you take dou u1 by, that is in terms of all the samples, u1, y1, x1, then u2 function of y2 minus beta 1 minus beta 2 x2 like that. So if you differentiate y1 with respect to u1 with respect to y1, it is 1. u1 with respect to y2, it is 0. Similarly, in the second equation, dou u2 by dou y1 is 0. So in the diagonal elements, you have 1. Off diagonal elements are 0. So this will be an identity matrix. In the single equation model, in the single equation model, this will be an identity matrix. Then we can write f y as equal to fu. Only in the single equation model, when we consider simultaneous equation models, this is not an identity matrix. And remember this is the Jacobian. The absolute value of the determinant is known as the Jacobian. So, as this is an identity matrix, we can write Fy as equal to Fu. Fy as equal to Fu. And so, Fy is equal to Fy is equal to 1 by 2 pi sigma square n by 2 expected minus half into sigma square then u is y minus x beta transpose u transpose y minus x beta. Fy can be written like this: x minus y minus x beta transpose into y minus x beta. Now, this equation involves observations on y, as you can see, and also the unknown parameters. This involves observations on y and unknown parameters beta and sigma square. Unknown parameters beta and sigma square. Now, writing this Fy, if you write this Fy as, if we write Fy as Fy beta sigma square, it is a PDF. It is simply a PDF for the parameters beta and sigma square. If we assume that the parameters are known, y is not observed, it is simply a PDF. This point we have discussed in detail in a previous class. If we write it as L beta sigma square y, it is a likelihood function. It is a likelihood function. Means that it is the value of this joint PDF is a function of the parameters beta and sigma square. In this interpretation, it is a likelihood function and denoted it as L. So PDF if parameters are known, likelihood function if parameters are unknown. Now the method of maximal likelihoods chooses as estimators of beta and sigma square those values which maximizes the value of the likelihood function. The method of maximal likelihood chooses the values of beta and sigma square which maximizes the value of the likelihood function. Now So, and letting theta transpose as equal to beta transpose and sigma square. Letting theta transpose as beta transpose and sigma square. Theta tilde is the ML estimate. Theta tilde is the theta transpose as beta transpose and sigma square. Theta tilde is the ML estimator. That means theta tilde transpose is beta tilde transpose sigma tilde square as the ML estimator. Then, and this theta tilde is obtained by differentiating L with respect to theta and equating to 0. And as derivation is easy, in log terms we differentiate L and L with respect to theta, equate it to 0, as we have seen earlier. The derivative of L and L with respect to theta, the derivative of L and L with respect to theta is known as score, and written as S theta. Now, the maximum likelihood estimator theta tilde is obtained by S score is the derivative of L and L with respect to theta. ML estimator is obtained by setting the score to 0. Setting the score to 0 and finding the value of theta such that dou L and L by dou theta is equal to 0. Now let us see how we actually derive it. Now we write the log likelihood function L and L as equal to minus n by 2 ln sigma square minus n by 2 ln 2 pi minus 1 by 2 sigma square y minus x beta transpose y minus x beta. And theta has k plus 1 elements. In our case, theta transpose is beta transpose sigma square. K elements here plus 1. Now, dou ln L by dou beta is equal to minus 1 by 2 sigma square minus 2 x transpose y plus 2 x transpose x beta. Remember this, we have this result earlier. Is equal to 1 by sigma square x transpose y minus x transpose x beta and it means that 1 by sigma tilde square x transpose y minus x transpose x beta tilde equating it to 0 means giving specific values to these two unknowns. That will give x transpose y minus x transpose x beta tilde equal to 0 and x transpose y is equal to x transpose x beta tilde. Solving this, you will get a beta tilde as x transpose x inverse x transpose y, the same OLS estimator. As we have derived these steps already, I am not repeating it again. These steps are familiar to you. Now let me consider one more case. Dou ln L by dou sigma square is equal to minus n by 2 into sigma square plus 1 by 2 sigma raised to 4 y minus x beta transpose y minus x beta is equal to minus n by 2 sigma tilde square plus 1 by 2 sigma tilde raised to 4 y minus x beta tilde transpose y minus x beta tilde equate it to 0. That will give n by 2 sigma tilde square is equal to 1 by 2 sigma tilde raised to 4 u hat transpose u hat, because this is u hat transpose, this is u hat. So that sigma tilde square is u hat transpose u hat by n, a result which we have derived earlier. Result which we have derived earlier. So, wireless estimator and ML estimator of beta tilde is same. Whereas, wireless estimator and ML estimator of sigma square is different. Wireless estimator is unbiased, so ML estimator is biased. So this is ML estimation of k variable model. The only step that I have discussed additional is the transformation from Fu to Fi. Fi is equal to Fu into absolute value of dou u by dou y, known as the Jacobian determinant. All the other steps and procedures we have derived earlier.